Hi everyone, Mr. Graham here. I want to introduce you to our first real physics unit. Whether you're an on-level pre-AP or AP physics, we all usually start from the same spot, and that's going to be the study of motion. So our first real physics unit will be over the study of motion. Up until now, we've just been doing a little bit of algebra review, a little bit of geometry review, so that we can actually do the physics. But now we're getting into real physics, and we're going to start our study of real physics, actual physics, by studying the motions of objects. As you'll see as we go through the year, usually when we're learning about new concepts like forces, momentums, energies, things like that, rotations, usually when we study those kinds of topics, we relate them to how they affect the motions of objects. And so in physics, almost everything will boil down at some point to either the motion of the object, of an object, or the lack of motion of an object or a system of objects. So our initial foray into physics is going to be to study the motions of objects. And what I'm going to do to try to get you interested in this a little bit is talk about something that I have a lot of interest in, and that's the two Voyager spacecraft. In the 1970s, NASA sent out two spacecraft named Voyager, Voyager 1 and 2. Strangely, Voyager 2 was actually launched before Voyager 1 just because of, I think, delay issues due to weather and things like that. But they were both launched in 1977. That is now about 43 years ago. One was in August, so its launch date was just a little over 43 years. Voyager 1 was launched in early September, so we're coming up on the 43rd anniversary of the launch of Voyager 1. And what I'm going to, and obviously the motions of these two satellites were very important. When we sent them out, they only had enough rocket fuel. You know, rocket fuel is very expensive to actually get into space, and so you can't just carry an unlimited supply out into space. And so to get Voyager up to the speeds that they needed to get out of the solar system, that was one of the main goals. The main goal was to study the outer planets, Jupiter, Saturn, and beyond. And then a secondary goal was just let them fly out of the solar system and see what they see, essentially. It's a little more complicated than that. But to get out of the solar system requires insane speeds that you can't even really comprehend. Like many, many miles per second. That's how fast these things are going. But we couldn't get them that fast. We could get them a few miles per second, but not to the speeds that they actually are moving now. And so how did they do that? They used what's called a gravitational assist. If you ever take AP Physics C or a calculus-based physics course in the future, you actually learn about gravitational assists and how you can kind of use Jupiter or Saturn as a slingshot to slingshot our satellites to give them a lot more speed. And so you had to make sure that these spacecraft flying through the huge vastness of the solar system actually lined up perfectly, not just to study those planets, but then to actually use them to slingshot out into the outer solar system. And so what I got pulled up right now is a simulation of the trajectories of the two spacecraft. So I sped it up a little bit so we don't have to watch the entire 2-minute video, but I'm going to pause it towards the end to talk about something pretty important. So here is the Earth. These lines that you see are just the orbits of the planets as they go around the sun. On these scales, on the scale of the solar system, the Earth is almost invisible. It's very tiny. You might have seen pictures with the sun here, and then Mercury, and then Venus, and then the Earth, and they're real close together, and you can see them. Reality is not remotely like that. In reality, the distances between the planets are gigantic. If you were to look at the entire solar system from like a bird's eye view, you wouldn't even be able to see the Earth. It'd be so tiny. So anyway, here's the Earth. I'm going to hit play. When I hit play, it's actually going to start running the clock. And if you look in the bottom left here, you see it starts at 1977, and it'll run all the way up until a few years ago. So here we go. Earth's going on its way. There goes Voyager 2. Voyager 1 is launched. Notice the days and months flying by down here. The two spacecraft are going, I think, between 10 and 15,000 miles an hour at this point. We can get them up to those speeds with rocket fuel. But then again, to get to the insanely high speeds that you need to get them out of the solar system, to get them to the outer reaches of the solar system, you need to use those gravitational slingshots or gravitational assists. And they both end up using Jupiter in 1979, it looks like. 1979, so a couple of years after they left the Earth, they got those gravitational assists from Jupiter and then again from Saturn. Voyager 1 was actually sent out perpendicular to the plane of the solar system, so it was done after it saw Saturn. Voyager 2 kind of stayed within the plane of the solar system a little bit. And then it's just going, they're essentially going in a straight line now. These two spacecraft, they're the farthest things man-made from the Earth. They probably will always be for forever, pretty much. They're so far away from the gravitational pull of the sun at this point that they're pretty much just going at constant speed in a straight line. And we'll be studying that motion, that type of motions, constant speed in a straight line very soon. But what I want to show you here, because some students kind of get oops, no, I didn't want to do that. There we go. That's what I want to do. Some students kind of get bogged down when we start talking about motion, because this is like three-dimensional motion. Really, it's four-dimensional motion because we have three spatial dimensions, and then we can actually track the thing through time as it flies through that three-dimensional space. Now, it's not like the scientists just pointed them out there and shot them and hoped that they were going to get to where they wanted them to go. They had to know exactly where they were going, or pretty close to exactly where they were going to go. And so what they have to do is essentially, it's a little more complicated than this, but they essentially had to, let me bring up my pen. They essentially had to think of the solar system as a giant coordinate system with pretty much the sun at the origin. Now, this is a three-dimensional coordinate system, so kind of think of this as kind of going back into the screen and out into the screen. So you can maybe say this is the y-axis, maybe this is the x-axis, maybe this is the z-axis. That's when we do three-dimensional graphing, we actually call the other axis the z-axis. We won't do that in this class. Only in AP Physics C do we really get into that in high school. And then at any point during this trajectory, and they calculate this before they actually sent the spacecraft out, so they know exactly where it's going to go as long as they point in the right direction and give it enough speed. And so you can say at any particular time during its motion, that spacecraft would have a position in the x direction, a position in the y direction, and and we're kind of used to leaving it at that, your x, y ordered pairs. In this particular case, though, you'd also have a z direction for that position. And then you would know, if you knew its speed at that point, then you can just predict where it's going to be at all future times. So we know where Voyager 1 and 2 are going. They're pretty much going in straight lines. They're billions and billions of miles away from the Earth at this point. And they're going very, very fast, as we'll see in a second. Now, I point this out because I think this is cool. I think this is cool stuff. I think space, astronomy, there goes the bell. I think astronomy is really cool. It's very interesting, this vast scale, the vast size. I mean, these things were launched in 1977, and they are considered to be just now leaving the solar system. So over 40 years of traveling faster than the fastest bullet out of the strongest gun you can think of, these things are going that fast, and they're just now getting to the edge of the solar system. So it's pretty incredible. The reason I'm bringing this up is because our first real study of motion, which is our first real physics unit, will be the study of one-dimensional motion. One-dimensional motion at constant speed. Some students don't really think that's very interesting. They get a little bored. So I'm just preempting that with, when you want to get to the cool stuff, you want to talk about astronomy and things as they move through space. If you want to talk about cars driving through loops, things like that. Just any kind of interesting motion, very fast motion. I'm a fast car enthusiast. I have a fast car. I enjoy them, but I enjoy fast cars. But really, to understand how to study motion on these more interesting scales, you got to start from the most basic scale. And the most basic scale, we're going to be talking about, say, the x direction, the motion in one dimension, usually the x dimension, unless you're talking about something in free fall. We can say that's the y direction, because that's our y-axis direction. We got to talk about that type of motion. We got to learn about that type of motion, and then we can build on that in the future to talk about these more interesting types of motion. So keep that in mind whenever you start giving Mr. Louise or Miss Coons or Miss Lee or Mr. Graham, myself, a little bit of grief over why do we have to study motion in one dimension. Well, you can't build. We build on that. You can't really talk about Voyager. You couldn't work at NASA and say calculate exactly where the Voyager is going to be, 100,000 years from now, unless you started your study of motion on the very small scale, in the very simple scale, motion in one dimension. And we are going to start not even with speeding up or slowing down motion. That's called acceleration. We're just going to talk about one-dimensional motion at constant speed. And so there's my introduction to the unit. Something else I wanted to point out. Come on. Just there's an interesting website. This shows you, it keeps up real-time stats of the Voyager 1 and 2 spacecraft at this point. If you look at the distance from the sun, Voyager 1 is about 14 billion miles from the sun at this point. Voyager 2 is about 11.6 billion miles from the sun. That's pretty far. That's a longer distance than you can probably really even comprehend. They've both been going about 43 years. Look at the speeds. Voyager 1, fastest thing humans have ever built, 38,000 miles per hour. And to kind of give you a feel for that, look at this number right here. That number, the distance from the Earth or the distance from the sun, that's real time. Watch those numbers climb. Look how fast those numbers are changing. That is how fast that thing's going. That's faster than, again, the fastest bullet you can ever think of. So incredibly fast objects. If you know, the cosmic speed limit is the speed of light. Nothing travels faster than the speed of light. It takes light, the fastest thing in the universe. It would, if you were to shine a laser at the Voyager spacecraft, it would take about 21 hours for that light to actually reach Voyager 1. So it's incredibly fast. And we're still getting data from these things. So the data that Voyager 1, if that's going to send a bit of data to NASA scientists and it leaves right now, doesn't get here until 21 hours later, almost a full day later. That's how fast those things are going. Anyway, so that's my introduction to the study of motion. There's the bell again. And I hope it was interesting. Hope it sparked your interest, and remember this video whenever we're studying one-dimensional motion at constant speed, because it's not quite as interesting, but we must build on that before we can get to the more interesting stuff. All right, that's about all. Have a good day.